Okay, great. Hello, everybody, and welcome to this edition of the Motivic Geometry Seminar. Today we have Michael Temkin, who will talk about logarithmic resolution of singularities. Please, Michael.
Okay, thank you very much for inviting me. Yeah, I'll talk about recent advances in resolution of singularities, but still probably most of my talk, or at least half, will be concerned with ideas of classical singularity, of Hironaka. It sort of turns out to be not that horrible as people thought, and I thought before I studied it. So now we have good understanding of this, and actually we already started to generalize the methods, and with many interesting twists. So this talk is okay. Logarithmic resolution of singularities' main goal was to resolve morphisms, and not just varieties. For morphisms, it's very natural to switch to logarithmic setting, and actually it's a must. This is the topic. Okay, now this is a joint project with Abramovich and Wlodarczyk. Everything I'm going to talk today. Yeah, as I told, morphisms and logarithmic varieties, because the context must be logarithmic. In fact, it's also must be stack theoretic. We'll get to this in the end of the talk. Yeah, but one has to leave the category of usual schemes for sure. References. Maybe I forgot to mention, I am using slides, but they're also available in chat. I provided a link. So if you want to go further or whatever, sometimes it's convenient that simultaneously you have an access to the slides. Okay, so references are two papers. One was in archive in 2017, and another one is relatively fresh. The first one was about absolute setting, but with logarithmic orbifolds and with logarithmic algorithm. And then the new one was about morphisms. So I'll state the general results about morphisms, but for simplicity, all ideas will be illustrated in absolute case, because actually this is the same algorithm, as I'll tell soon. Second, I'll just touch a bit functorial embedded resolution while weighted blowings up. This is interesting because actually there is no logarithmic geometry at all, but using stacks and weighted blow-ups, which were discovered during our logarithmic studies, we are able to prove Hironaka's resolution in a much better way. Again, I'll mention it a bit during the talk, but it will be just a tangential topic. Good. Now, classical resolutions. So in introduction, let me just recall a bit about what all this is about. So for simplicity, we'll always work with varieties over a field K of characteristic 0. Also, also will no. Okay, well, anyway. One can also work analytically over C, or in fact, even some non-Archimedean field of characteristic 0. Okay, now resolution of singularities takes an integral variety Z and produces a modification, which is proper operational morphism from Z-res to Z, where Z-res is smooth. Z-res is resolution of Z. Hironaka, in his Fields medal work in 1964, proved that resolution exists. Just exists. It was existential proof. It was not constructive. In the 70s, Hironaka and Giraud simplified and shaped some ideas which were inside the proof. Hironaka's proof was very complicated, and people started to understand it. It took decades to really figure out what are the main points, where in particular maximal contact was shaped in the 70s. Villemaillard and Bjornstam-Millman in 80s, 90s actually provided for first time algorithmic and canonical resolution. So it was done by algorithm and not just existence of the proof of not just existence argument, and it was done canonically, but is compatible with any automorphism of variety. In particular, it's automatically equivariant for group actions, which is a large advance. And then Wlodarczyk in 2005 proved that actually it's smooth factorial, which means that it's compatible with any smooth morphism Z prime goes to Z. The resolution of Z prime will be pullback of resolution of Z. It's more strong than canonical. It's compatible with any smooth morphism. Okay, good. Now about relative and logarithmic resolution. So classical algorithm, as we proved in 17, has a logarithmic analog. For log, it takes a log variety, which is generically log smooth, and it modifies it in such a way that X resolved is log smooth. We provide it as a stack, so the modification is not representable. It's a stacky morphism. But then we manage to make this resolution functorial with respect to any log smooth morphism y to x. And this is very strong functoriality, stronger than in classical situation. In particular, this is this functoriality that establishes the property that log smooth locus of x is not changed. In a recent preprint, we actually extended. We take the same logarithmic resolution algorithm and proved that it works for morphisms. Given a morphism x to b, there exists a map x res to x such that x res to b is log smooth. There is one small catch. This algorithm can fail if dimension of b is larger than 1. But it fails for obvious reason. If dimension of b is larger than 1, we might need to modify b too, because in such case, b has modifications, and sometimes you must also modify both x and b. So the new gradient is a claim that there is a large enough modification of b, which I denote h b prime to b, such that the algorithm does not fail after base change to b prime. And moreover, it's then compatible with any further phase change. So in fact, the algorithm is relatively functorial. It's not functorial on B. There is no canonical modification of B. But once we take large enough modification, the usual algorithm, which we first of all developed for varieties, works even for families. So that's the new ingredient. Now, if f is proper, and only in this case, if x to b is a proper morphism, h can be chosen canonically. At least this is work in progress. So we are working on it yet. It seems to be correct, but not in general. And it's not written down so far. Good. Now the plan of this talk will be, we'll first of all talk about classical resolution. And then we'll talk a bit about log geometry. Probably I'll skip some parts of log geometry because I assume that in this seminar, people are familiar with some basics of logarithmic geometry. So maybe we'll go faster. And then I'll explain about logarithmic algorithm and what are its difference and similarities to the classical algorithm. Now, from now on, we'll work only with logarithmic, in logarithmic setting, only with varieties. So I'll explain the algorithm from 17. As I told you now, this same algorithm works for relative setting, but it's more technical, and for a talk, it's not good to have too heavy notation and so on. So, but essentially, the logarithmic algorithm is the one which works for families. Good. So let's start with embedded resolution. Okay. So from Zariski, I think, and definitely from Hironaka, Biancar, and the classical method of resolution of singularities is okay. Well, let me say it as follows. So before our work, there existed just essentially one canonical method. It grew on ideas of Hironaka, was shaped by Villemayor and Gersten-Millman, after them Wlodarczyk. Descriptions were different, but the algorithm was essentially the same, up to small combinatorial differences. Also, once we construct canonical algorithm, it can be constructed locally. If you construct something locally and prove that it's compatible with open immersions, you can glue. Or maybe even you can work it out locally if you prove that it's compatible with smooth morphisms. So proving canonical algorithm or constructing it is often easier because everything is local. You just work with local chars. And in this talk, we'll only discuss this situation locally. And all these algorithms are built on embedded resolution. That is, locally, one takes variety X we want to resolve, embedded into an ambient manifold, which is, by manifold, I always mean here smooth variety, and then works with the pair M and the subscheme X. So to this pair, one associates a sequence of modifications of ambient space when blows up the ambient manifold, and then wants to take the pullback of X. But the preimage of X under blow-ups of M typically will contain copies of exceptional divisor, so it cannot be smooth by any means. We want to take transform, which is a bit finer when just pull back. So typically, we'll consider transform which removes a copy of exceptional divisor. We'll discuss it later. But we are not taking full pullback, we take some transform. Functorial embedded resolution implies functorial non-embedded one. It's stronger claim because embedding is essentially unique, locally, and so on. Up to some technicalities, you can prove independence of the embedding. So from now on, we'll only talk about embedded resolution. We are given ambient manifold M and something embedded into it. Now, what are the choices of the classical algorithm? So I claim that actually there are many choices which are often thought of to be something a must to take. And in fact, they are not. So it's important for me to stress what are all choices that people are doing in classical approach. So first choice is to take class of modifications. The algorithm actually blows up smooth submanifold, and then another smooth and another smooth. Why? For a very simple reason. If we blow up something uncontrollable, a general ideal, then M will become non-smooth, and we'll lose any control on the ambient manifold. Yeah. On ambient manifold, we will want to work with coordinate, usual regular family of parameters. It's important for us that it is smooth. So we cannot lose with smoothness. We must blow up only smooth submanifolds. Transforms. As I said, the transform is constructed very simply. We just pull back X and subtract a multiple of exceptional divisor. We'll talk later about which multiple, but typically just each time we subtract some multiple of the exceptional divisor. Choice of centers. What is how it is done? So typically we'll want to consider some invariant, and the primary invariant is very crude. It's just order of ideal. I'll give some examples a bit later, but morally it's just minimal degree of generators of this ideal. So it's very crude order, and it's a big surprise that it works, but it works only because of sort of induction we'll immediately discuss. Another complication and another choice one has to do in Hironaka's approach is that if we just use naive order, as we'll see in a couple of slides, you'll get two loops. If you just take the locus where the naive invariant looks the best one and blow it up, you'll get the same singularity and you'll go to the loop. So you must keep history back and remember that what you have done before. The algorithm works only with history. History is encoded in exceptional divisor, which we collect throughout our resolution process. And the number of components of exceptional divisor at a point, so the history of a point is sort of another primary invariant. So in fact, the algorithm will run by induction. We first of all study situation in M and associate the pair of D1 S1 of primary invariants. That is the order of ideal and the number of exceptional components. Yeah, so first of all, we look at order. At the locus where order is maximal, we look at the number of exceptional components so that it is maximal. After that, we restrict to a smooth submanifold of codimension 1 called maximal contact. I'll describe later how it is chosen. In the maximal contact, on the restricted ideal, we'll take its order and number of exceptional components, and so on. So in principle, the invariant is something relatively simple. It's just lexicographically ordered string, order, number of components, order, number of components, and so on. Questions about the structure of... Okay, don't hesitate to stop me and ask questions if needed, yeah? Especially in slideshow, you know, it's easy to lose audience. Okay. Now history and what I call dream algorithm. So classical algorithm has a subtle inductive structure and it encodes the history, as I told. And with our choices, no history algorithm does not exist because of the following example. So example of no progress. Let's take ambient manifold just A4. Okay. And let's take something is going.
Maki, there's a question for you in the chat.
Yes. Let me see.
Where does normalization come in?
Which normalization? I did not do any normalization in my.
Normally, you blow up and you normalize, and you blow up and you normalize.
No, I don't do such a thing for sure. In non-logarithmic setting for sure. And okay, is it the screen is shared? Yeah or not? No, it's not shared. And even if I resolve a curve, I'll not resolve it by normalization. I'll resolve it by blow-ups, because curve, even singular curve, is embedded into a smooth surface, and there is no normalization of surface. I can only blow up surface, and on the curve, it will restrict to some blow up of a curve. So even resolution of a curve is a subtle process in this algorithm. And moreover, you'll see very soon, I pass from curve to ideal and I lose any geometric intuition of what's going on. So this method does not use normalization at all. Yeah, there is a risky method how resolve surfaces by blow ups, and normalization is different method. It's not embedded. Embedded method cannot use normalizations. Okay, did I answer the question?
Yes, thank you.
Okay, so okay. Somehow it, okay, well, anyway. Example. So let's consider this A4, and we have x given by vanishing of x squared minus yzt. So when the singular locus is just the origin, and there is a S3 action by permuting yzt. So we have no choice. What we must do, we must just blow up this. Sorry, the exceptional locus consists of 3 x's. I think y, x, and z. But the only equivariant smooth subscheme in the singular locus is the origin. So if our algorithm is canonical, it must blow up something equivariant. It must blow up the origin. When I blow up the origin, I just write down the equation for new coordinates on the chart. Instead of x, I'll get x prime, y prime. Instead of y, I get y prime. Z is y prime, z prime. T is y prime, t prime. And after taking outside y prime square, which is just y's exceptional divisor, I get the same singularity. So equivariant method must just blow up the same singularity over time if it does not remember the history. So taking into account history is the only way to get out of such examples. Another example, maybe even more famous, is example of this is example I learned from Jarek Wlodarczyk. A more classical example is Whitney umbrella. You can write down similar equations. These are the same degrees, by UA, and you'll get the same. So pinch point will persist when you blow up pinch point. But this was very striking discovery, which I talked about. A dream algorithm does exist if you use weighted blow-ups. So if we move to category of smooth stacks and we extend our allowed modifications from blow-ups with smooth center to weighted blow-ups, then we can construct algorithms which do not use history. It just takes maximal invariant locus, blows it up, looks again on what you have, blows it up, and so on. Such algorithm does not use exceptional divisor at all. It's not logarithmic in any sense, and it's more efficient and more, in a sense, more natural. It's the simplest algorithm you can imagine. You describe some singularity invariant, you prove its maximum is achieved, and you prove that it drops after blow up. But only in the realm of stacks this is possible. So it's, as I promised, it's tangential to our talk, but this should indicate that actually there is plenty of room beyond what was known until 17. Yeah, from Hironaka's work and until 17. So there are possible modifications, maybe other two. Okay. Now the boundary. By boundary, I mean the exceptional divisor, and exceptional divisor grows during our procedure. Yeah, even if we start with empty exceptional divisor, then after blow up we get some, and after another blow up we'll get the old one, preimage of the first one, and the new one, and so on. So it gets larger and larger, and it remembers what we have done. Now, exceptional divisor provides us God-given coordinates. Like here, if it's smooth, and when its parameter is unique up to a unit, it gives us a coordinate which we can choose in all our work, and this reduces the number of automorphisms, of symmetries of the system. So if I use such coordinates, I have less symmetries, I have a chance to avoid these loops. And this is how the algorithm really works. So inductively, for a sequence of blow-ups of M, we define this total exceptional divisor as preimage of the old one and the new one, accumulated boundary of it. Now, we always work with coordinates T1 up to Tn, such that the new center, so we choose coordinates over with new center, will be described as the linear space given by vanishing of few such coordinates. And the exceptional divisor at stage I is given by vanishing of product of last R coordinates. So it has R components, and last R coordinates actually define it. So we always take coordinates of exceptional hyperplanes to be the part of coordinate system. And if we choose centers in such a way, then we guarantee by a very simple computation that a new exceptional divisor will be simple normal crossing. We are not allowed to blow up anything. We are not allowed to blow up a center which touches exceptional divisor. This will make new exceptional divisor singular. But we allowed to blow up things which lie completely in some component or are transversal to the other components. So this is called that the new center has simple normal crossings with the old exceptional divisor. And accordingly to this, we say that there are exceptional coordinates and there are monomial coordinates. So the monomial are exceptional monomial. So exceptional coordinates are those which correspond to exceptional divisor, and the other one are sort of regular or free. So we have large freedom with choosing free coordinates, and up to units, the exceptional coordinates are fixed. Good news. So first of all, if we use these monomial coordinates, we have less choices, and we indeed manage to avoid loops. And construction is sort of more canonical. Moreover, this boundary part can accumulate a part of the ideal of X. So we can manage that if we denote I, the ideal of X, we decompose it to monomial part, which is product of few exceptional divisors, and pure non-monomial part, the ideal which cannot be divided by any monomial parameter more. So this splitting is used all the time through the algorithm. And in this sense, we want to transform ideal from purely non-monomial to purely monomial. So the algorithm is realized as monomializing or principalizing the ideal. Bad news, which actually is the same coin from the other side. We must treat E and monomial coordinate with a special care. Yeah, I must keep E as and C, so I have less choices. Sometimes it helps, sometimes it's a problem. And yeah. Okay, a remark. As I explained, in fact, we have two types of coordinates in the algorithm. And many technical complications of classical algorithm is that they are not separated well enough inside the algorithm. The order of ideal involves both usual coordinates and the monomial ones. So it's a sort of spoiler. I already explained you what will be improved in the logarithmic version. Okay. Principalization. Now, all algorithms work algebraically, as I told in my answer to the question. We switch from X to ideal, and we solve the following principalization problem. We would like to find a sequence of blow-ups which keep M smooth and E simple normal crossing. So where the pullback of ideal becomes invertible and monomial. So just divisor supported on exceptional divisor. Yeah. So just product of few monomials. Magic trick due to Hironaka is that when we do the last blow up where strict transform of X is non-empty, yeah, I want to stress that when I achieve this situation, strict transform is empty. I started with empty E, and if I manage to do it, preimage of X is contained in the exceptional divisor. It means that strict transform just was killed during this operation. So the last time the strict transform was non-empty, it's easy to see. I'll not explain it, but it's really, really easy that actually this strict transform was equal to the center of blow up. Since we only blow up smooth centers, it means that at this stage, strict transform was smooth. So resolution is achieved one stage before principalization is achieved. Yeah. So moreover, it even achieves that this VL, it's transversal, it has simple normal crossing with the boundary. So it achieves the situation that XL is smooth and the boundary, the exceptional divisor restricted to XL is simple normal crossings. It indicates that actually there is some logarithmic structure inside, encoded inside. Non-formal, but sort of indication. And okay. And now working with ideals gives us a lot of flexibility, as you'll see, because we can pass from one ideal to another. And ideal can correspond to a non-reduced scheme. And we don't care. Once we are in realm of ideals, we'll not worry for geometry of these ideals. Okay. Now let me explain how this order reduction is achieved. The main invariant of the algorithm, as I said, is the degree order, D. It's just minimal order of elements which generate the ideal. For example, if I have x squared minus yz squared, the order is 2 because of x squared. And if I have ideal x5 plus y7 x cubed z cubed, when the order is 5 because of x5. So it's something very, very naive. And typically, since the ideal is decomposed as monomial part and non-monomial part is our friend. It's already monomial. It will stay monomial after. So we only worry for non-monomial part of the ideal. Also, in Hironaka's works, he called it idealistic exponent. It just assigns to ideal I this number D, this order. And call it marked ideal or weighted ideal. Maybe weighted ideal is the most precise. We view this I with some weight D. Now, you can ask why should I fix D and not just take the IPO, order of IPO? The reason is that in our algorithm, we'll use induction and restriction to hypersurfaces of maximal contact. And when we restrict, we must remember what the order was before. So because of induction, we must suffer a bit more, and we must take possibilities for different Ds, and not just D equal to the order. And one only uses blow-ups with centers, so that the order along with center equals to D. So we only blow up the locus where the order is at least D. And in this way, we achieve that after we blow up, we can remove these copies of exceptional. This condition implies that the pullback of I can be divisible by this power of exceptional, of ideal of exceptional divisor. So our transform will be always remove these D copies of exceptional, because we only blow up where the order is D. And the goal is to get the situation where the order of I drops below D. So we cannot blow up anything more. In this case, we'll solve that, say that marked ideal ID is resolved. For example, we computed such case for this equation a few slides before. Now, order reduction, yeah, as I said, is just sequence of such blowups. They're called ID admissible. D is a part of this datum, and we want in the end to get the I with no points of order D. If we solve such a problem, when principalization follows, we can just take D equal 1. So principalization is particular case. Okay. Now the case when D equals to order of IPO is the main one. It's called maximal order case. And the general case is implied relatively easy by some combinatorial reduction, which is even possible in any characteristic. So maximal order case is really the main one. The other one we just take into account because of induction reasons. Okay, good. Now the most subtle thing which exists in the resolution of singularities. Yeah, so far I just outlined you a general strategy, but it's natural strategy, I would say. So nothing surprising, probably. Maybe except this trick with principalization implies resolution, but the real magic is existence of maximal contact, and this is the only thing which is completely breaks down in characteristic P. So here we come to something subtle, which actually works only in characteristic 0. So the miracle is that we want to run induction on dimension. For this, we want to take singularity and consider a hyperplane which approximates it as well as possible. And more precisely, we only consider this weighted singularities with D in the maximal order case. So we only want to consider this locus or singularity, this multiplicity of the singularity. And it turns out that a resolution of marked or order reduction of marked ideal I, D in maximal order case is equivalent to resolution of certain ideal C of I, which I'll define now in some example, restricted to a hyperplane H and of order D factorial. Because of this, actually, instead of resolving I on M, we'll resolve C of I on H. This gives us induction on dimension. C of I is called coefficient ideal, and H is called hypersurface of maximal contact. It has maximal contact with singularity. So main example, and actually it's crystal clear. It's very, very simple. It really can be done by hands if you spend a bit more time than I have in my talk. Let's consider I given by vanishing of one equation. So it's a hypersurface given by vanishing of T to the D plus A2 T to the D minus 2 plus AD, where T is the first parameter and AI depend on T2 up to Tn. Yeah. So let's assume we are working in AN, and this is given in this way. In such case, we have that maximal contact is just vanishing locus of T. yeah, the order, I assume the order is D. And coefficient ideal is just ideal generated by coefficients with correct weights. So typically we want A2 to be weight 2, AD weight D, and so we normalize by weights. We have to take the power D factorial to be able to divide by 2, 3, 5, and so on up to D. So to put these weighted guys in a single ideal, I must raise my order to D factorial. Yeah. Okay. And so a couple of remarks. So why I restrict to H using coefficient ideal? Well, the answer is simple. If I just restrict I to H, I'll get just AD on H, and I ignore all the information contained in AIs. This is stupid. It's obviously that it cannot work. So we lose information. So a smart way to restrict is actually to take all coefficients to relevant powers. So in characteristic 0, I can achieve A1 equal 0, like this happens here. And okay, we'll see soon this is absolutely critical. In characteristic 0, it comes for free because D is invertible. Okay. And after this example, I'll describe a general strategy, and it uses derivations. So main tool for a description of the algorithm without any choice is to use derivation ideal. D of I is generated by all elements of I, it's generated by I, and also by, oh, it's missing here. It should be, and all derivations, sorry, by elements of I and all their derivations. And when we can derive ideal a few times, getting D to the n of I, iterative derivation. Now, please pay attention that the order of I drops by 1 when I derive the ideal, because in characteristic 0, it's more or less obvious. Just look at Taylor series of elements and find derivation which reduces the degree of, yeah. So it's sort of obvious observation. And now using it, I can reformulate the notions I introduced before in absolutely canonical way. So the order of I is the minimal D such that this derivation equals to O of X. Yeah, because any derivation just reduces by 1. Maximal contact is any hypersurface given by a regular coordinate by an element of order 1, which is contained in D minus 1 of Ix. So because of this condition, such maximal contact always exists. There are plenty of them maybe, but at least one exists. So you can choose, check in the previous example that all these obviously holds. The coefficient ideal. Again, I just used derivations of I and took them with appropriate weighting. And again, I think that I is a weight D and I'm first derivative is a weight D minus 1 and so on. And the only serious difficulty in proving that this algorithm works and works canonically is choice of maximal contact. This is not canonical. You might have many choices. This is a sort of headache. This is the most subtle point, which I'll not touch in this talk. But all the rest is I more or less described to you the algorithm, what you should do. So at least on the level of blocks, we already have all blocks. We consider ideal, we consider its derivations, we form these guys, and we have induction on. Okay, now maybe one remark now about log derivations. So there is also a model of logarithmic derivations, dlog, which is spanned by mj, dmj, and dti with respect to regular coordinates. So these are precisely the derivations which preserve E. They take ideal of E to itself. For almost everything, which when you want to prove things and so on about or make computations, logarithmic derivations are more convenient to work with. The only reason why the usual algorithm cannot work with logarithmic derivations is that the order is computed using all derivations and not only logarithmic ones. So, okay. Now, And because of this, actually, the algorithm has two complications. Maybe I'll not stop too much on these complications. I'll just say where we are supported, but I'll not where we are located. I'll not discuss about solutions. In the end, it's less important for this talk. So first complication is that we must respect our E, our exceptional divisor. But the maximal contact does not have to be transversal to E. So it may happen that we cannot restrict E to H. Just it makes no sense. It's not simple normal crossing anymore. So in case E is touching to H, one must do something more smart. And in fact, because of this, the solution is to consider to stratify E by multiplicity, by how many components of the boundary you have through the point, and to work with with strata of larger multiplicity first. So classical algorithm, this secondary invariant S shows up because this complication. Now, this complication will be gone in logarithmic algorithm, so I don't want to spend time on explaining how it's resolved, but it causes to some headache, and the algorithm is more long because it's invariant, takes into account all these numbers of components all the time. Second complication, it might happen that the order of I is larger than D, but the order of pure part is smaller than D. In such case, we cannot improve pure part, and we must take into account also the degree of monomial part. And again, it causes to some we must look at pieces given by stratification, by multiplicity of exceptional divisor. And again, this is the thing which does not show up in logarithmic. So I just wanted to mention that this bad separation of logarithmic parameters and regular parameters show up again and again in usual algorithm. And it causes to the algorithm to be more complicated than what I'm going to describe now. Okay, so there is some resolution. I'll not talk how it's done. Okay, good. Now we are done with classical, and I want to motivate towards the logarithmic. So let's try to understand what actually boundary is. So before I studied this topic, I thought that a boundary is a divisor. It's a subscheme, and at least ideologically, it's wrong. At least I think so. So I don't think that we should view E as a subscheme. We should view it as a logarithmic structure, as I'm going to explain. And for example, when we have a blow up, M prime, E prime goes to ME. E prime is the new boundary. There is no map from E prime to E. It might happen that we started with empty E and we produced a boundary. So even on the level of functoriality, we do not treat exceptional divisor as a divisor. We don't have a map of divisors. We have inverse inclusion. The preimage of E embeds into E prime. So this is functoriality of logarithmic structures. Now the boundary is determined by sheaf of monomials. By logarithmic structure induced by E, I denote it monomial induced by log E. It's just notation, this log. These are all elements of OM which are invertible on the complement of E. Yeah, so just units and the monomials. It's generated by units and monomials. So this gives rise to correct functoriality. When we blow up and blow up and blow up, the exceptional the monomial gets larger and larger. Okay, moreover, in our algorithm, as I explained, actually what we need from the exceptional, we need monomials. We need monomials to decompose or to principalize our ideal. So we really only need monomials. So we work with logarithmic structure. Okay, locally, this guy, as I said, is splits as units and times free monoid. Just the number, generated by M1 to MS. Okay, now a couple of words about logarithmic varieties. I'll go very fast through it because I assume some familiarity. Yeah, so it should be sort of known at some level to the audience. So logarithmic variety, yeah, it's variety and structure sheaf and sheaf of monoids, yeah, logarithmic sheaf with a homomorphism to O of x, which induces isomorphism on units of this monoid and units in OX. Well, morphisms are defined naturally. We don't need too much of this. We need only basic example when we have x, we have divisor d on x, and monomial structure is just induced by units outside of d. Yeah, just like the example we have seen on manifold with simple normal crossing divisor. In such case, morphisms just correspond to morphism x prime to x. So the pullback of d is embedded into d prime. So also geometrically, it's something very clear. Many constructions extend to log geometry, construction of logarithmic sheaf and logarithmic differential derivations I talked before. These are just logarithmic analog of usual derivations. There is also a notion of logarithmic differentials, not only derivations. Theories look very similar in a sense. Morally, one just adds logarithmic differentials, which are dm divided by m. So this equation just says that delta m is dm divided by m, logarithmic differential of m. There is a notion of log-smooth morphisms, and typically, as one should expect, they can be characterized by local freeness of relative differentials of expected rank. So theory of schemes in many aspects generalizes to logarithmic varieties, and especially theory of smoothness. It generalizes very well. And this is what we need. Yeah, we are doing resolution of singularities, and we want to generalize notions of smooth things, smooth morphisms, and so on. So everything generalizes to log smooth. Moreover, for resolution of morphisms, log smoothness is essentially important because it's known, it's well known that you cannot resolve morphism just by a smooth one. You already in semistable reduction type theorems, it was discovered that you must allow some singularity of morphisms, some semistability or something. And the natural class where you can hope to resolve morphism is log smooth morphisms. So this is the reason why log geometry seems to be just the context to discuss resolution of morphisms. Okay. Classical example of log smooth things are toroidal varieties. So in old language, this was just described by toroidal varieties. Okay, so in a sense, logarithmic geometry generalizes toroidal geometry to non-smooth setting. Okay, what is important is that locally, log smooth varieties, formally locally, can be described as follows. Just formal power series in T1, TL, which can be viewed as regular parameters, and M where M is a monomial, is a monoid. In the earlier situation, M was free monoid. It was generated by M1 up to Mn, the monomial, the exceptional parameters. In general log geometry, M can be any fine saturated monoid. So monoid can be general. We have less control on monoid. And because of this, from now on, we announce monomial democracy. From now on, we don't know which element of M is good and which element of M is bad. So all elements of monomial structure called monomials, they will be equally good for us. Yeah, in characteristic PBOI, this is not the case because there are piece powers and not piece powers. But in characteristic 0, all monomials are equally good. And what is important for us is just to know basis of MGP. For example, base of omega can be described by dt1 up to dtn, and any base, any logarithmic differentials of a base of MGP. So we can use powers of monomials or whatever. Okay, good. Well, this probably I want to skip. And maybe, okay, maybe just one example which I want. Again, this is just repetition of what log smooth morphisms are. I assume that we are familiar with it a bit. But I would like to give one example here of log-smooth morphisms. So log et al. Cover obtained just by extracting roots of monomials. For example, extracting roots of parameters which define exceptional divisor. Such a cover is smooth in logarithmic geometry. So our algorithm will be compatible with such covers. And this is something which is absolutely unnatural and impossible in usual resolution. So although I am discussing now on next slides, resolution of logarithmic varieties or even usual varieties, the functoriality is much stronger. It's functoriality even with respect to such covers which are Kummer log et al. Covers, or more generally log smooth morphisms. So our algorithm must be very different in some aspects. Okay, now let's see how yeah, this is the remark I just made. So now let's see how it goes. Okay, logarithmic algorithms. So first of all, main results. So I'll come in the last slide to orbifold aspects, but so far I ignore something. So I put something under the carpet. Yeah, so, but up to this, what we want to do is the following. We want to take toroidal variety, or log-smooth variety, just the same language. Log-smooth variety with an ideal I in OX. This is what was earlier denoted M, but now M is also logarithmic structure, so I cannot use M too much. So this X is ambient log-smooth variety. There is an ideal in OX, and we want to find a sequence of admissible blowings up. I'll describe what does it mean. Of toroidal variety, so that all guys in the middle are toroidal now, log-smooth. Even if I start with smooth, in the middle I'll get log-smooth, but not smooth. I'll not keep smoothness, only log-smoothness. And I want this last guy to be monomial, be just ideal with generated by monomials. And such thing exists, and the sequence is compatible with any log-smooth morphism x prime to x. As in the classical situation, this actually implies resolution of any integral logarithmic variety z. For any such z, there exists a canonical 0s to z, which is log-smooth. How you prove it? You embed log variety into log-smooth one. You take its ideal. Yeah, you embed it by strict morphism of log varieties. You take ideal and you principalize it, and this follows. So the reduction from here to here is like in classical theory, it's similar. So I'll talk now about log principalization. The method. In brief, we want to adjust all parts of classical algorithm. So on purpose, I formulated them in such a way that it will be easy for me to adjust them. And in fact, at first approximation, we just want to use log derivations instead of usual derivations. So I'll put log, log, log everywhere I can. Let's see how it goes. Log order is the minimal d, so that d logarithmic of ix iterated d times is the structure shift at the point x. So just I don't guess, we'll see that there are some surprises. I even don't care what is the meaning of this log order. I just give the definition, copying the old one, but in logarithmic world. Maximal contact, absolutely the same. We just take regular parameter t in d minus first derivation. And when vanishing of t defines something log smooth, so we can restrict to it and run induction. Coefficient ideal, same story, just take weighted sum of derivations. In addition, the only thing which I must explain, what does it mean to have I, d admissible ideal? The definition is very simple. We just want I to lie inside J to D, where J is any ideal generated by a family of regular parameters and any set of monomial parameters. For monomials, as I said, we have democracy. I do not control them. They are not responsible for order, as you immediately see. I don't care. I can take large ideals. Fortunately, I can take any set of monomials and blow them up. And even if I don't have T's, if I only have monomial ideal, then blow up of monomial ideal is even log et al. Morphism. So it produces something which is toroidal automatically. It's even logital morphism. And this is, by the way, a bit surprising difference between usual theory of schemes and theory of fine or FS log schemes. In category of fine FS log schemes, any monomial blow up is logital. So such blow up produces still a log smooth outcome. X prime is still log smooth. And the transform is defined because if I is contained in J to the D, then its pullback is contained to J to pullback of J. This guy is the exceptional, so I can divide by its D's power and define the transform. We call such ideals submonomial because they are monomial on a submanifold, on a logarithmic submanifold given by vanishing of few regular parameters. So you can check that this condition I belongs to J to the D is equivalent to the admissibility we have in classical setting. Okay, good. Now surprise. Yeah, we have a couple of more minutes just to finish, and yeah, we are almost done. First surprise. So logarithmic order of usual coordinates is 1, as you can expect. But logarithmic order of monomials is infinite. Maybe this is the main novelty. And this is not that horrible. This just says that monomials are sort of not so informative for our algorithm. We are free to do whatever we want with them. Please pay attention. If I have a morphism, a Kummer cover, given by extracting root of monomial, then the order of monomial upstairs and downstairs must be the same if the algorithm is compatible with such covers. The only way to achieve this is to declare that order of all monomials is infinite. It cannot be any number just because of compatibility with Kummer covers. And moreover, by our definition, to find the log order of monomial, I must take its log derivation. But any log derivation just multiplies by a number. You'll never get to 1 starting with monomial by log derivations. You can only get to 0 or to some multiple of m. So its log order is infinite. Because of this, we must deal separately with the case when log order of ideal is infinite. It turns out that this is very simple, and in fact, it was done before us. It was done by Kolar. He asked how you could resolve ideal on toroidal variety by monomial blowups. And the answer is very simple. If, for example, I is generated by a sum MITI, just take all monomial coefficients. Yeah, they actually generate the minimal monomial ideal which contains I, and blow this up. And after you do it and divide by the exceptional divisor, you'll get one power which has no monomial coefficient anymore. So you just get rid of monomial coefficient in some place, and you get finite log order. So to start our process, we do such a monomial blow up. After that, log order drops to something finite, and we can run the algorithm. So it's simpler. It avoids both complications I told before. And it completely separates, as I promised, regular coordinates, which are dealt with by log order, and monomials, which are dealt with by combinatorics. And the invariant now is just the string dn up to d1, the orders. I don't care for the monomial stratification. There are no number of exceptions from my point. So just such a thing. So it's, in a sense, it's much faster. D can be infinite. In such case, you apply such a step. Good. And where is the cheating? Yeah, I promised the orbifolds. Okay, so the point is that the algorithm does not distinguish monomials and their roots, as I have just explained. Because of this, the algorithm sometimes says that it wants to blow up this power of monomial, the power which does not exist on our manifold. For weight reasons, it sometimes wants to blow up m to 1 over d. Now, this can be bypassed by working on Kummer covers. So you can say, okay, let's consider Kummer cover, where this root is extracted. Yeah, the algorithm is compatible. So let's walk upstairs, do an operation, and then divide back. But when you divide back, you get something which is not log smooth anymore. And because of this, we divide back in a stacky vault. So we define this Kummer blow up as a stacky modification, a weighted modification. In fact, we prove that classical weighted blow up can be enhanced to blow up in vault of stacks, so that the stack is smooth. It's coarse moderate space. The classical weighted blow up is singular, but the stacky blow up is smooth or log smooth, depending in which setting you work. And okay, and just one example. Since I'm over time, I'll just put it on the board, and that's it. So very simple example where already in dimension 2, where you see that you must also were related by this functoriality. You see that in one case you can blow up T and M, and in other you'll have to blow up T and M to the half, and this produces non-representable Kummer blow-ups. So already in simplest cases, non-representable blow-ups show up. As I told somewhere in the middle of the talk, this has huge advantage actually to generalizing or improving Hironaka's algorithm using these weighted blow-ups. We proved this dream algorithm exists. So this is a feature and not a bug, and I hope it will be useful for operational geometry in the sequel use of non-representable modifications. And that's it. Thank you for your attention, and I'll be glad to answer questions.
Okay, thanks a lot, Michael. Let's all give it up for the speaker. So you didn't mention de Jong's technique of alterations. Does that play a role at all in this theory? Or
in this, de Jong cannot play. Okay. Well, one of our motivations for this project was to bypass de Jong. Yeah, so in a sense, it played a role. But you know, if the only resolution of morphisms in general dimensions was done by Abramovich Caro, it was done by de Jong's technique in their paper in Vinsons in 2000. And because of de Jong technique, it's not canonical, and when modify the smooth locus, if you have a morphism with generic smooth fiber, you must modify even generic fiber. You don't have control. So our motivation was to bypass it by canonical methods. So, but in de Jong's method, if you dig inside what you have the same flavor of logarithmic geometry and of even maybe of stacks. If you don't want to take alteration, but only non-representable modifications of the base, you can do it by. So same tools actually are also basic in de Jong's same context of logarithmic geometry and of even of stacks to some extent. You find them in de Jong's theory, but only these tools, not the structure, not algorithm, and not And moreover, de Jong goes by fibrations, and we go by cutting, by codimension. In a sense, it's it's opposite inductive scheme. Okay.
Okay, thanks. Other questions?
Oh, sorry. Could you explain again in the main theorem the modification Z res? Is it a log schema or it is not representable?
Let's go. It's okay. Well, I say it in the end. Maybe here. Let's see. Letter can be okay. Remove stacky structure. It is log scheme, and it is a stack, both. Now, after that, you can ask, okay, for my applications, maybe I don't want neither this nor this, so I want to remove them. To consider few more modifications, which will get rid of stacks and of and get a log structure which is smooth. Yeah, both are possible, but are less functorial. Yeah. So when you remove stacky structure, it's called destackification. It's in fact, it goes back, I think, first idea to Abramovich and de Jong. After that, Abramovich and torification, and after that, there is a paper, destackification in general by Reed and and whole, I think. And it's sort of we have to introduce these tags because coarse modular space can be singular. Yeah. So if we would like to work on the level of coarse modular space, making just usual weighted blow-ups, we'll get to singular stuff, and there is no good way to compute orders and to work and to take. So we enhance them to sticky level. But you might ask, okay, can I find now a phase of modification of stacks so what coarse modular space becomes smooth? And this is possible. It's called destickification. Yeah, and if I achieve this, I can just ignore sticky structure and get back to coarse modular spaces. This is possible, but it's not functorial with respect to logarithmically smooth morphisms. More correctly, it's not functorial with respect to Kummer covers. It's functorial with respect to part of them. We describe explicitly to so-called saturated ones, but it's not compatible with respect to Kummer covers. So as far as I understand, what we are doing in this generality, it's the minimal generality, which allows you the natural functoriality. Now, once you get this log smooth coarse modular space, you can ask, can I now resolve it combinatorially just to smooth? It means that you want to resolve monoid to a free one. It's like toric resolution. There are well-known algorithms how to do it. So from that stage, you can even go to just a smooth guy. It will be even less functorial. It will be functorial only with respect to smooth morphisms. So classical theorems are implied, but the other stages will be were well known before. How to proceed from log smooth orbifold with diagonalizable. Yeah, our algorithm only introduces diagonalizable inertia. With diagonalizable inertia to smooth coarse spaces. Yeah.
So to verify that I understood correctly, so in general, it is orbifold, but for the classical setting, it implies the classical result.
No, but even in general, even if I start with orbifold, once I get this resolution, it's achieved by log smooth orbifold with diagonalizable inertia. And then there is a classical, not classical, okay, there is something called destickification. There are few approaches how to do it, destickification, which produces a new modification, a larger modification. Yeah, modifies this log smooth one to another log smooth one, which has log smooth coarse modular space. Okay.
Okay.
So you can get good coarse modular space. Now, if we started with something which was a variety, then this coarse modular space will be modification of your initial variety. So it will be resolution of initial variety. Okay.
Yes. Yes, I understand. Thank you. Oh, and may I ask also one
Sure.
another question? In the positive characteristic case, can you explain with many details what holds and what doesn't hold?
Well, people in resolution like to say that only maximal contact does not exist, but in principle you should think about this that nothing exists. Yeah. So all the rest are sorts of reductions, but the central thing does not exist. So well, okay. We try to see if this weighted stuff adds us some flexibility and so on, but still non-existence of maximal contact is
Understand. Okay.
Yeah, it kills everything. So yeah.
Thank you.
Any other questions?
I have a question about the relative statement.
Yes.
So you say that okay, let's suppose you just apply the algorithm and you get something log smooth. Let's say this happens, and let's not worry about this.
Let me just, I'll open this theorem. Sorry, no, it was embedded. Just a minute. Same logarithm. Yeah. Okay. Yeah. So okay.
So yeah, so let's say we just applied this algorithm and okay, we have
Yes.
something. Okay, so is it, so I guess in general, we cannot hope to get a smooth morphism.
Yes, for sure. Already for curves with bad reduction, this is the best example.
Okay, but is it clear when is it possible to find a resolution that is at least LCI? Or does this sort of relative statement shine any light on these kinds of questions?
Okay, I'm not well prepared to answer. I know that there is some work by recently by Chesnovicius, and he achieves only normal stuff, maybe only Kohn-Macaulay 2. And already this was done. Okay, I'm not that sure. I'm not that sure which. So let's say so. On one hand, you can always get there is classical result that any singularity can be resolved to something which is hyperplane. Yeah, so it's LCI. It's something very mild from one point of view, but if you want to do it canonical and so on, then I think even Chesnovicius maybe did it just for S2. I don't remember, but he wanted to get something very mild, and it was already a non-trivial work. So non-canonically, everything is equivalent to hyperplane. Yeah, but okay, I don't have anything better to say.
Okay, thanks.
The last chance for a question. Doesn't seem to be the case, so let's thank Michael for a very nice talk again.
Okay.